In the pursuit of extending human health span, few therapeutic strategies have drawn more interest or more complexity than the use of senolytics and autophagy modulators. These two approaches, while distinct in mechanism, converge on a shared biological target: the accumulation of damaged, dysfunctional cells that drive aging and increase cancer risk. Senolytics aim to eliminate senescent cells, those that have ceased dividing but refuse to die, while autophagy enhancers aim to restore the cell's internal recycling and repair system. When used thoughtfully and in tandem, these therapies may offer a way not just to slow aging, but to reverse some of its cellular consequences. However, the path is not without serious warnings and unresolved risks. Senescent cells are a hallmark of aging. They arise in response to DNA damage, telomere attrition, oxidative stress, and oncogene activation, acting as a natural safeguard against unchecked proliferation and tumorigenesis. In the short term, this response is protective, but in the long term, the accumulation of these cells becomes toxic. Senescent cells secrete a cocktail of pro-inflammatory cytokines, matrix-degrading enzymes, and growth factors known as the senescence-associated secretory phenotype, SESP. This SESP damages surrounding tissue, fuels chronic inflammation, and alters the microenvironment in ways that promote both tissue degeneration and cancer initiation. Senolytic drugs, such as dasatinib and quercetin, have been developed to selectively induce apoptosis in these lingering cells. In animal models, their removal leads to impressive outcomes: improved tissue function, enhanced physical performance, and reduced markers of inflammation. In some studies, senolytics also lower the incidence of age-related cancers by removing cells that sit on the edge of malignant transformation. Yet the process is inherently risky. Senescent cells, though harmful in excess, also serve roles in wound healing and tissue repair. Eradicating them indiscriminately may impair regeneration or trigger unintended compensatory responses, especially if the underlying cause of senescence, such as genomic instability, remains unresolved. This is where autophagy comes into focus. Autophagy acts earlier in the damage response chain. Rather than waiting for cells to become senescent, it repairs or eliminates dysfunctional organelles and proteins before they destabilize the genome. In a youthful state, robust autophagy keeps senescence and cancer at bay. But with age, autophagic efficiency declines, allowing more damage to accumulate, more cells to enter senescence, and more inflammatory signals to propagate. Enhancing autophagy pharmacologically, with compounds like rapamycin, spermidine, or N80+ boosters, can therefore act as a preemptive form of cellular maintenance. In doing so, it reduces the burden on the senolytic system and may even reverse senescence in certain cases. When combined, senolytics and autophagy modulators could form a powerful anti-aging synergy. Senolytics remove the cells that have passed the point of rescue, while autophagy boosters restore functionality in those still salvageable. This dual approach has been shown in animal studies to rejuvenate organs, improve cognitive function, and even extend lifespan. By clearing away cellular clutter and restoring metabolic balance, these therapies reestablish a healthier internal environment that resists both degenerative disease and malignant transformation. However, translating these findings into human therapy is still in its early stages. Senolytic drugs must be administered intermittently to avoid off-target toxicity, and their long-term safety is unknown. Autophagy enhancers, while generally less toxic, may have paradoxical effects in cancer. In early stages, they help suppress transformation. In established tumors, they may allow cancer cells to survive under treatment-induced stress. This double-edged nature demands careful timing and precision. Enhancing autophagy in an aging population with dormant or undiagnosed tumors could theoretically awaken hidden malignancies, especially if senescent cells are removed without restoring immune surveillance or repair systems. Another challenge lies in tissue specificity. Different organs accumulate senescent cells at different rates, and autophagic decline varies by cell type. The brain, liver, and skeletal muscle all show distinct aging trajectories, and a therapy beneficial in one tissue might be neutral or harmful in another. Future therapies will likely need to be targeted not just by disease but by organ system, biological age, and individual genetic makeup. Nevertheless, the potential is profound. For the first time, science is approaching the ability to not only treat the symptoms of aging, but to systematically clear the dysfunctional cellular debris that causes it. Senolytics and autophagy modulators are not mere life extension gimmicks. They represent a shift in how we understand and address aging as a modifiable, partially reversible biological process. Yet they must be used with restraint. Aging is complex and multi-layered. Its interventions must be grounded in biology, not ideology. A therapy that rejuvenates one person may destabilize another. Cancer risk may fall in some tissues while rising in others. The goal is not immortality but integrity, to preserve the function, resilience, and dignity of the aging body without triggering unintended consequences. In conclusion, senolytics and autophagy-enhancing therapies hold great promise as tools to clean, restore, and rebalance aging tissues. When calibrated correctly, they may reduce cancer risk, delay frailty, and restore metabolic harmony. But like all powerful interventions, they must be handled with foresight, selectivity, and an evolving understanding of the complex dance between damage, repair, and renewal that defines the aging process.